in today's tutorial, we are going to look at the last part of triple and double integrals. The method that we're going to look at is known as the change of variables type method for these double and triple integrals. Now, the way these questions are set out, the first one's actually not that easy. So I'm going to go to 139 and start with that one because I feel that's the actual easiest one to do. And I'll show you why as we go. Now, change of variables, just like the integration you saw at school, or maybe in first year, it's all about taking a complicated integral, perhaps in over a complicated region, and simplifying. Simplifying the integrand and simplifying the region of integration. So that's the motivation behind it. So the basic change of variables formula is the following, right? You've got some sort of, let's say for double integrals. Let's say you've got some difficult region, difficult function, and you want to calculate the double integral. So t of d is just some set, t is here some operator, and f some function. Now, under the change of variables formula, what you do, instead of integrating over this potentially difficult region, you just look at this set D. You make a substitution for the x and y variables, say in terms of u and v, and you adjust the integrand by throwing in this determinant of the Jacobian. Okay, so there are some assumptions, of course, that we make on our operator t. So let's just quickly review those. Firstly, t's a one-to-one mapping. The determinant of the Jacobians, not zero, or if it is zero, it's only zero at sort of isolated points. So it might be zero at the origin and zero nowhere else. Okay. We also make some assumptions on our f, g, and h. For example, if f, g, and h all have continuous partials, that's another assumption that's sort of embedded into the mix here. So okay, and there's just some standard assumptions on your t. I'm going to write all those down. So again, the idea is to take something that's complicated, make a change of variable, and reduce it to a simple situation. Okay, so that's the change of variable. And you know, there's the natural extension to triple integrals and so on. Now, an interesting idea here is how does this formula relate back to single integrals? So if you have a bit of spare time, go back and go, oh, how does this relate with the stuff that I learned at school or first year university? That's a good exercise. Anyway, we'll come back to this in a second. So the first question I'm going to do is actually 139. And as we go through it, I'll actually show you why it's simpler than, for example, 137 or 138. We'll do those ones as well, but the method is a little bit trickier in those ones. So 139, we're given the substitutions u equals some function of x and y, and v equals some function of x and y. We're asked to determine the area of this region omega that's bounded by these curves, or the curves associated with these equations. So how do we set that up in terms of our change of variables formulae? Okay, so I'll come back to this in a minute when I need it. All right, so to put the notation, the same notation as was on the previous slide, I'm going to let omega just be this. And the question tells us that this region is bounded by the following curves. And what we're asked to do is calculate the area. Well, you might think, well, why don't I just go through and calculate the double integral over that area? Well, one of the problems is that these areas may not, or these regions may not be simple regions, okay? So they're hard to do in terms of just regular double integrals, describing them. So let's take their advice and use the substitutions. So we're asked to let u equal x plus y and v equal x minus y. So our equations here will then simplify. They're going to become the following. So we're going to get, that'll be v, so I divide there, I'll get v equals u squared on 4 and v equals 1. Now, notice that under these substitutions, we actually don't have what we want here. Here we've got x equals a function of u and v. Up here I've got u equals a function of x and y. Here I've got y as a function of u and v. Here I've got v as a function of x and y. So what I'm going to do is actually rearrange these equations and make x the subject and make y the subject. So I'm going to get x in terms of u and v and y in terms of u and v. Now, that's pretty simple in this case, but in general it can be quite hard to do. For example, in question 137 and 138. So you need to sort of be a little bit more careful there. And I'll show you how to do that in a minute. Okay, so if I just add these two equations together, I'm going to get something like, and rearrange, I'm going to get something like x equals u plus v all on 2. So that'd be your g of uv. And if I take one equation away from the other one, I'll get y equals u minus v on 2. So that then is your h function. Okay, well, we're getting there. So we thus have the following. So operator t is just defined by these two functions here. So let's just write that as a sort of a column. And we get something like this. Okay. So what we're asked to do is calculate the area. So let's draw the sketch of the region in the UV plane. So D is bounded below by this curve, which is going to be a parabola, and above by this sort of line here. So if I draw in my dodgy looking parabola, I get something like this. So this then is my region D. Now, of course, my in the XY plane, it may look totally different. Okay, so now what? Well, you can find the intersections here and here, and if you do that, according to my calculations, you should get 2 and minus 2, basically just making this equal to 1, and v equals 1 in here, and just rearranging. So our region D that we're interested in is just u between minus 2 and 2, and v greater than or equal to 1, less than or equal to u squared on 4. So let me just adjust that. So v's got to be less than or equal to 1 and greater than or equal to u squared on 4. Thank you very much. Because if I draw any vertical line, I can see v enters at this and it leaves at this. So yeah. In this case, because we're calculating the area, our f is just identically equal to 1. Okay, so what I do need to do now is calculate the determinant, or the absolute value, the determinant of this, of the Jacobian of this. This is going to be 1 in this case because we're calculating area. I need to calculate the determinant of the Jacobian. So here's my t. Let's calculate the Jacobian. All right, so if this is my t, what's the Jacobian going to be? Well, it's going to be a 2 by 2 matrix. I just want to take the gradient of that and write it as a row. So if I differentiate this with respect to u partially, I'm going to get a half. If I differentiate this with respect to v partially, I'm going to get another half. If I differentiate this with respect to u, again partially, I'll get a half. And again, if I do it with respect to v, I'll get minus 1/2. So now what I want to do is take the determinant and then look at the absolute value. So if I take the determinant of this, remember it's just this times this minus this times this, and then I want to take the absolute value. I get something like negative 1/2, and take the absolute value, I'll get 1/2. Okay. Now I can finally apply my change of variables formula with f identically equal to 1. This is going to be a half, and I'm just integrating over my d. So the area of the region in the xy plane is just this. We know this from one of the basic properties of double integrals. Now under the change of variables, I can change this to this and replace the 1 in here with this and integrate. Now remember, this is just a half. So let's put in my limits of integration. They come from down here, assuming we've done it correctly, of course. So using this, I know that I'm going to integrate from minus 2 to 2 and from u squared on 4 to 1. This is a half. What are we going to have here? dv du. Okay, now you might think, how did I switch those? Well, I haven't fixed the order of integration, so I can just write that down whichever way I like. Okay? If you want to write that down dv du, well, feel free to do so. All right, so this is just a constant now. So I can actually take that out the front, do the inside integral. The inside integral is going to give me something like 1 minus u squared on 4. And then if I've just got a single integral here. So if I do that single integral, I'm going to get u minus u cubed on 12. When I sub in my u equals 2 and u equals minus 2, my calculations give me 4/3. So that sort of brings together all the stuff that you know about double integrals. Questions? Now, it was reasonably easy from that substitution to rearrange and make x and y functions of u and v. It's not always the case though. Okay? It's not always the case. So I'm going to do a question now where you don't have to do that. You don't have to rearrange your substitutions. Okay? It's quite good. It's quite a good time saver. I mean, the problem with having to rearrange the equations is when you see this, you would go, okay, let's make u equal this and v equals this. But the change of variables formula is when x equals something involving u and v, and y in something involving something involving u and v. So it's actually a little bit reversed. Okay? So that's something to be mindful of. So I'm going to do (138), and then I might go back and do 137. Anyone done 138? Anyone? 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 No? Okay. We're asked to find the area again of some region in the first quadrant of the xy plane, which is bounded by a set of curves. Now, I look at this, and the substitution I want to make should simplify the boundary, the description of the boundary somehow. So if I let u equal x squared plus 2y squared, then I get u equals 1 here. That's a pretty simple curve. That's a pretty simple line. If I let u, and here I'll get u equals 4. So what I would like to do is somehow make a substitution for, involving v and simplify these pairs of lines. What sort of substitution could I do to make these lines constant? Any idea? V equals something involving x and y. Y on x, okay. If I let's say I rearrange this and put the x down there. If I let v equal y on x, then that equation there will give me v equals 2, and that equation there will give me v equals 5. So you're absolutely right. Okay? So that's a good mental note. When you're looking for substitutions, when the substitutions aren't given to you, you want to try, in many cases, to make substitutions where you get just constant lines. That's a information. Okay, so let's see if we can do this. Yes. So this is 138. All right, so I'm going to label my set, T of D, in the xy plane by this. know what T or D is yet, but I'll adjust those as we go. Hang on, I've left off a 2. So there should be a 2 in there. Okay, so let's make those substitutions that you suggested. Now, I'm going to introduce this phi function. And this phi function is actually going to be the inverse of the t operator. Yeah, I could write t inverse there, but I'm just not going to, and just have it. You can if you want to. Okay. So what will D be under this substitution for U involving U and V? Well, let's look at the bounds. If U equals this, then U is going to be between 1 and 4. And if V equals Y on X, then I can sort of change these around and I'm going to get V between 2 and 5. Now that's just a rectangle. That's a filled rectangle. So we like working with those because they're simple to integrate over and they're simple to draw. Okay, so in the UV plane, our set D is just a filled rectangle, which is nice. Okay, so let's just do a quick drawing of what's going on here. Here's the UV plane. Okay, it's drawn a little bit dodgily. Now, what does it look like in the XY plane? Well, let's look at the boundaries. Here I've got x squared plus 2y squared equals 4. That's going to be an ellipse. X squared plus 2y squared equals 1. That's going to be an ellipse. And these curves are not too hard to... Are these just going to be straight lines? They're just on the boundary. So, according to my calculations, you'll get the following. You'll get something like a line here, and you'll get two arcs of a ellipse. Okay, if you calculate the intersections, you should get something like this. Again, drawn rather dodgily. So your T of D is just here. Okay, so think of T mapping between the two coordinate systems. Okay. So what we want to do is calculate the area here. But again, this doesn't look like it's a very simple region. So what we're going to do is we're going to integrate over here and use the determinant of the Jacobian to sort of balance things out a bit. All right, so the area of this red shaded region, as we know from the basic theory of double integrals, is just this. Now this double integral is hard to calculate, probably because the region T of D is not simple. It doesn't appear to be simple. So what we're going to do then is use our change of variables formula, again with f just identically equal to 1, and integrate the following over D. Now here's the tricky thing. I want to calculate the determinant of the Jacobian of t, right? But I don't have t anywhere. I've only got this, the inverse of t, denoted by this phi thing. So can anyone suggest how we might actually calculate the determinant of the Jacobian of t involving the determinant of the Jacobian of phi, of its inverse? Anyone know? Oh yeah, who said that? Yes, what is it again? Can you speak up? I know it's cold. Can you speak up a bit? Okay, so the determinant up here of this Jacobian may be calculated by using the following. Now, was that discussed in lectures? Okay. You can prove it just using the chain rule. Okay, remember here, phi and t are just the inverse of each other. Okay, so if you sort of pull this up to the other side and actually just remove the determinants, you can use the chain rule for Jacobians to sort of multiply them together, and you know you've got to get the identity, and the determinant of the identity is 1. The determinant of the Jacobian of the identity is 1. But anyway, if you don't want to prove it, don't worry. This is important. Okay? So let's work out this, and then I've got this. That's pretty good. One small problem though. All right, so here's our phi. Let's work out the determinant of the Jacobian. Well, let's take the gradient of this and write it as a row. The first is going to be 2x, then it's going to be 4y. Down here you're going to get something like minus y on x squared, and down here you're going to get 1 on x. So, the determinant of this it's that times that minus that times that. So if you do the algebra and write it in the following way, plus 2. Now, the problem with this is that I really want that, x squared on y squared. Y squared on x squared, sorry. The problem with this is that up here, you want this thing here in terms of u and v. And I don't have it there, I've only got it in terms of x and y. But for this particular example, I can just sub out y on x because I know v equals y on x. So I can just replace this with 4v squared. Hang on, I made a mistake. Yeah, you're right. So that should be jt. Okay, sorry about that. Okay, so if I just substitute this for, replace it with v, I'll get that. Okay, that's good. That's what we want. Okay. All right, so what I can do now is knock over, hopefully, my double integral. All right, so the absolute value of this is just going to be the same thing because it's always positive. If I take a factor of 2 out, I'll get the following, 2v squared. Now, I've got my region of integration D here. It's just this rectangle. So I can find my upper and lower limits, etc. of integration. Let's take that half out to the front. And I'll get something like this. Okay, so do the inside integral first. You can see that the integrand doesn't depend on v at all. So it's just look at the difference here and just sort of remove the middle. So you're going to get something, 4 minus 1 is going to be 3, so take that to the front. And I'm going to get something like this. Okay, so to integrate this final integral, it's going to be something involving tan inverse, right? So if I write it like this, let's just change that to, say, the following. Then I can write it the following way, just using tan inverse. So all I need to do now is sub in my upper and lower limits of integration. And I should get the following. Okay, so this is really a great method for solving these problems where you don't have the actual exact form you don't have this form here. Okay? All you really need to do to compute this is the determinant of this Jacobian. And you can calculate that using its inverse.